Hello and welcome back to another episode here of the Hidden Quantum Champions. Error correction is one of the most pressing problems in today's quantum computers, and it is crucial to solve that. Today's journey takes us to Singapore to Entropica Labs, which is trying to solve that on the software layer. And if you're interested in learning more about that, join for today's video as we dive right into Entropica Labs. So with that, here we are on the website and it says software tools for fault-tolerant quantum computing. Hashtag productizing software for fault tolerance, hashtag error correction software. And that's exactly what it is. And we can also see here some images and I think, or some schematics, and I think that also is to illustrate that is probably available for different platforms. So we see the classical chandelier setup here, which is, I think, indicative for the superconducting quantum computer. But we also see something here, which looks maybe a little bit more like a photonic thing. Here we see something that is a little bit more like a crystal, so it might be some neutral atom kind of approach. And that one here looks like a I don't know, could be a silicon chip or something. So maybe different type of approach as well. But let's not speculate. Let's move a little bit on what the website says. So Entropica Labs solving the quantum error correction QEC problem is the key for the future of quantum computing. Our software stack enables hardware teams, researchers, and developers to design error correction codes, inject quantum error correction logic, and run programs fault-tolerantly in real time. Quantum computing can't scale without quantum error correction software. To make fault tolerance a reality, the industry needs tools to deploy error-corrected programs across real hardware. That's what we are building. So here's the stack, right, or the diagram. The upper layer says tame the complexity of quantum error correction design. Then next layer is fix errors before they cascade. And then it says guaranteed fault-tolerant execution, which lead into turning high-level code into hardware-ready, error-corrected, executable quantum programs. And before we move on, maybe one step back. So why is error correction so important? In a quantum computer, you benefit from two different effects that are kind of innate to quantum mechanics, which is the idea of superposition and entanglement. So superposition is the idea that you can be in a superposition or in a state between two states. So instead of saying your logical bit is 1 or 0, you say it can be 1 and it can be 0 at a certain probability. And the other effect is called entanglement, and that is a relationship between two different quantum systems. So if you, for example, create an anti-correlation, you would say if one bit is 0, the other one's 1. And now this entanglement, that makes things actually quite complex, because if you have an entangled system, you can entangle two, let's say, qubits with each other, but then you can entangle a third one via the second one. And if you really want to make use of this whole, let's say, complexity that the quantum computer can calculate, you actually want to spread your superposition as far as possible across your architecture, more or less. And in order to do that, you are running all of those gates, which might collect some errors. There can also be some bit flips due to cosmic radiation. I think there was some great research from MIT showing that. So there are all types of ways that errors can accumulate. And now these errors, they start locally. So you might flip one bit in the wrong way. You bring it in a superposition where you actually didn't want to create a superposition. But then as you entangle those, they kind of spread across your whole system, like globally. And that's where it becomes critical, because suddenly you cannot just say, okay, maybe that part was faulty, and then we kind of disregard that, but it spreads across the whole system. There's another issue that comes along with that, which is the idea of non-cloning theorem. So the idea says you cannot just copy quantum information. So I mean, what does it mean, right? If I have a bit which is 1 or 0, I can just copy it by saying if it's 1, then my other bit is also 1. The problem is with quantum mechanics is once you read out a bit, a quantum bit, you actually flip it, you actually project it into one of those states where it doesn't necessarily have to be that. So if you say you prepare the qubit in a way that it's 70% 1 and 30% 0, and now you want to copy that information, you need to measure it, right? And when you measure it, it collapses into either 1 or 0. So you can only measure one piece of information. And then if you copy it, of course you have the same thing. You can kind of make sure that your other qubit is also 1, but you're losing the quantum property because previously it was not 1, but it was 70% 1 and 30% 0. And that's kind of more or less roughly the idea of this non-cloning. And that is on the one hand a cool feature if you want to create secure quantum communication channels. So that's, let's say, an idea that goes into quantum communication. But then of course it makes it difficult to create something like a parity bit where you just, let's say, read out all of the information and then create one that is kind of different to the others, because you cannot just read out the information in between. You cannot just go ahead while you're running your algorithm and then you say, okay, now I copy this piece of information and then I continue with my cycles, right? So the idea of error correction is extremely complex when it comes to quantum computers. There's a whole set of research behind that, and it's not actually easy to implement. And even though you see that the number of quantum bits are scaling, so maybe 10 years ago we had 2, maybe now we have 200, something like that, right? Even though that is scaling, it doesn't necessarily mean it's easy to kind of now put the error correction on top and everything is solved, right? So there are also different levels of error correction. And it might be meaningful, it might be a good idea to have some company that has expertise in that. Might also be interesting for quantum companies to integrate an expert team like this one, right? But this is now me interpreting stuff. Let's move back to the website and see what they are actually telling us here. So our product, design, wave, orchestrate one software stack for the entire life cycle of quantum error correction. The operating system for fault-tolerant quantum computing, a unified software stack supporting the full quantum error correction lifecycle from code design to runtime orchestration, making large-scale quantum computing commercially real. So, code to runtime, that is, of course, an interesting idea, right? So in the code, you would write your algorithm, like, for example, the Shor algorithm. You would implement that with your gates, maybe the Clifford gates, gate set or whatever. And then this needs to be translated into runtime. That's my assumption now. So kind of what has to happen in terms of which signals have to be sent down to the chip. So there's always like a layer below, right? And I think if I understand that correctly, it goes even one layer below just saying, okay, here are the Clifford gates. This is how you integrate the error correction. So then we see here Loom Design, the open source toolkit for quantum error correction. Learn, design, explore, validate. Bring quantum error correction to life with Entwine's drag and drop UI and Loom's programmatic power. For students, educators, and researchers, Loom Design makes quantum error correction visual, intuitive, and practical, turning theory into hands-on exploration. And here you can now see how that would look like. So what do we see here? Well, first of all, it's very abstract, but my interpretation of what it is. So this is a two-dimensional lattice here. So we see the different dots here, and they are all kind of interconnected. That could, for example, be a chip with quantum bits. So you had like one of these being one qubit, the next one being the next qubit, and they're all somehow connected to each other in this specific topology here. So in this lattice shape. Of course, there are also other lattice shapes. If you think, for example, of graphene, the interconnection between the different dots would look a little bit different. So there are different ways of connecting these dots. Could also be triangles, right? But here in this case, we have this square type of lattice shape. And now what you can see here is with a drag and drop kind of approach, you're now connecting those tiles with each other. And I think that is kind of how you would actually build your, within a drag and drop approach, you would actually build this this kind of error correction or circuit approach. And you can also see here on the right side, it generates the code that is being, generated from the drag and drop operations that you're doing. Here it says define lattice surgery circuits with a few mouse clicks. Then there is also some testimonials here. So you see Quantum Machines as a user or a testimonial, and you also see Xanadu linked here as well. So how we support you: a toolchain for fault-tolerant quantum development. We help you manage the complexity of quantum error correction so your teams can focus on what they do best. Our software supports your work across research, development, and system planning. And there's like 4 components that we can see here. One of them is QC hardware teams, software teams, research institutions, and then enterprise strategy teams. So I think these are the 4 different tiers that we are that are being targeted here, right? So on the hardware teams, it says evaluate architectures to support fault tolerance, integrate quantum error correction into your system roadmap, prototype and test logical qubit architectures, estimate resource overheads and performances. Then on the software side, which are probably the people that are kind of working on programmings or algorithms for quantum computers, it says develop reliable hardware-ready quantum programs, compile high-level logic in quantum error correction-ready programs, simulate, debug, and evaluate your code, apply reusable quantum error correction design patterns. Then on the research institutions, it says turn theory into scalable outcomes, design and simulate new quantum error correction codes efficiently, run simulations for logical circuits, prepare experiments that run on real hardware. And then finally, for the enterprise tier, it says plan your entry into fault-tolerant quantum computing, identify suitable use cases and required capabilities, assess internal skills, timelines and requirements, align quantum adoption with your business priorities. And then the call to action: get started today. Our software is available for early access. And as mentioned before, the company is based in Singapore. With that, let's quickly check out the technology stack that they have in terms of software. So we saw already before there's some open source stuff going on here. I think very interesting, helps very much to spread the word, makes it easy for the companies to start using it. And then of course there will also be stuff on top of that, like for example this Loom design here, which I guess is then gonna be a paid kind of upgrade on top of that. So what we do, building the backbone of fault-tolerant quantum computing. At Entropica Labs, we are productizing fault tolerance, creating modular software tools that simplify quantum error correction from design to execution. Our integrated stack supports the full quantum error correction lifecycle and lays the foundation for our long-term vision, QLID, the Fault Tolerance Operating System, FTOS. At its core, it's Loom, our flagship platform that converts quantum programs into fault-tolerant, hardware-ready circuits and connects every layer of the stack, enabling scalable, error-corrected quantum computing and paving the way towards QLID, our future FTOS. So the aim is to build an operating system on top of, let's say, quantum computers. So I guess zooming a little bit out, what we have today is NISQ, so noisy intermediate state quantum computers that have certain properties, that have certain noise innate to them, and that is not corrected, right? So you can run algorithms, but you will reach some kind of limit at some point, because you would either have to optimize further your qubits. You have to make them better, and then still there will always be cases that kind of can create problems, right? I mentioned cosmic radiation before. The other thing is like the systems are at very low temperatures, at least for the superconducting ones, right? But also for the ions, you have to cool them down. But there's also always some temperature influence still there, right? So you have to kind of shield your system from the temperature influence from the outside and from all types of effects. And it becomes more and more challenging. There is also this idea, and that's when you look at different quantum platforms, there are some which have very long coherence times. So they're very, very well shielded from the outside. So they can, for example, in diamonds, they can remain coherent even at room temperature. But then it's actually not so easy to kind of control those qubits because they are so well shielded. So it's not so easy to kind of flip them into a different state in a very controlled fashion because they are kind of hidden in a box or in a very well isolated box. There are other ones that are less well isolated. You can control them very fast, like superconducting qubits. You can operate them on radio frequency types of signals. But then on the other hand, their coherence times are also much less, so they're not so well shielded. If you kind of counterbalance both of them, that's where you see that certain systems, they are performing very similarly well on that scale. And that's why we still see that there are many different systems that are being, let's say, set up and experimented with today, because there's no clear winner in this kind of race. There are ongoing further ideas, like for example the Majorana-based approach, so using states that are, let's say, that are by their nature fault tolerant. But this is, from my point of view, as somebody who kind of worked in those types of materials, still in a kind of early stage. So if it works, it's like a moonshot type of thing. It would be very cool, but it's not 100% clear that it works. Whereas for these kind of systems, superconductors, ions, and many others, silicon, spin qubits, it is already kind of proven that you can build qubits out of these, that you can operate these, and that they fulfill the Loss-DiVincenzo criteria that a quantum computer needs to fulfill. But all of that just to say, so you have these NISQ type of systems, and now the idea is to put a layer on top to make these NISQ qubits logical qubits. Logical qubits are now kind of software optimized qubits that perform exactly the way that they do in the textbook. So you can, run an operation on them, leave them on idle for a long time, and they will not just flip. They will not just change their property. That's the promise of this error correction. That's the promise of these FTOS, more or less. And today we are not there yet, right? But there are a couple of tools, and this is what we can see here. So Entropica tools, our model stack is structured around 3 core pillars of fault-tolerant quantum computing. Number 1 is design. So create and visualize quantum error correction codes with intuitive interfaces. And there's Entwine, we've read about that before, an integrated development environment, IDE, for fault-tolerant quantum circuit design, build, run, and analyze quantum error correction circuits in a single self-contained graphical environment, enhances learning, experimentation, and demonstration of quantum error correction. Then there is EDB. EDB transforms quantum computing experiments into large-scale collaborative projects. It enhances individual and team workflows by making data organized and accessible. EDB supports structured shareable data workflows, long-term experiment tracking, and multi-user coordination and data reuse. So that's, I think, more like on the research side of things, whereas that one is on the science communication, error correction communication, and then learning, experimentation, demonstration side of things. After design, there's Weave. Transform high-level quantum programs into fault-tolerant hardware-ready circuits. And there's Loom that we've seen before. So the core of our software stack, Loom connects the algorithmic layer with hardware and control systems automating the transformation of quantum programs into scalable, executable, fault-tolerant circuits. Automates quantum error correction, code design and analysis, accelerating the path from code definition to threshold computation, translates logical quantum error correction code instructions into their corresponding physical level fault-tolerant circuits, and then generates hybrid quantum classical code for hardware execution. And that's, let's say, what then goes onto the system, right? And then there is EK, a library designed to preserve the context of low-level quantum error correction instructions from Sanskrit 1 or first. EK provides a data structure that serves a single source of truth throughout the entire execution of a quantum error correction code, fully serializable, queryable, scalable, and programmable. EK facilitates the design and execution of error-corrected quantum computations. And then finally, there's the orchestration layer. That's going to be, let's say, the operating system, right? So execute and scale fault-tolerant quantum applications, QILT in development. The FTOS, QILT, is it will unify the entire stack, manage and execution, adapting to different hardware backends and enabling seamless orchestration of quantum applications. And then there's some points here on Loom design again. What you can do is learn and teach. We've seen that before, right? Explore lattice surgery with an intuitive visual interface. That's this one here that we've seen, I think. Design and build prototype codes or use ready-made templates. That is the code that we see on the right side. And then experiment and validate. So simulate noise, test fault tolerance, and benchmark thresholds. And that's, I guess, what you see here with this Jupyter notebook, where you can play around, tune a little bit the noise sources and see how effective your error correction code actually is. And now a quick step back, as per usual. If you are interested in learning more about that, or if you actually want to have a tutorial on that, if you want to see how that actually works, how to do that, as always, let me know down in the comments below. I will reach out to them and we will do a tutorial if possible and if you're interested. Why Loom design? So it's an open source and quantum error correction focused approach. It's dual interface. We've seen that before, right? Coding and visual, and it's end-to-end. Learn, design, and validate. And then here we see the team behind the company. Why Entropica Labs? Useful applications of quantum computing will only become possible with fault tolerance. At Entropica, we simplify the design and testing of quantum error correction, making it easier to integrate fault tolerance directly into quantum programs. With deep technical expertise and modular tools, we are unlocking practical, scalable ways to work with quantum error correction codes. And then, as per usual, you see the call to action here. Quickly checking out the news section as well. As per usual, I'm recording that end of January 2026, and you can also see there is some news here from 2026. Entropica Labs and Giacomo, I'm not sure if I pronounced that correctly, sign MOU to advance system-level co-design for fault-tolerant quantum computing. And there is more if we scroll down here. Like, for example, the quantum machines collaboration. There's also some involvement with the Qiskit Fall Fest, and so on and so forth. Let's quickly, as per usual, also check out the teams part here to see who are the people behind the company. So at Entropica Labs, our mission is to build the software stack for fault-tolerant quantum computing, transforming quantum machines into engines of discovery. We're advancing the foundations of this technology so that knowledge can move faster, deeper, and further than ever before. Without fault tolerance, quantum computing can't scale. Our vision is a world where the full power of computing unlocks new knowledge at unprecedented speed, driving humanity forward. The values of the company are truth over ego, apply knowledge, discover together, and ship courageously. And that is, let's say, how the setup looks like. In the background, we also see the team here. Truly a team. Meet the Entropica team. At Entropica, we are a group of scientists, engineers, and curious minds working to make fault-tolerant quantum computing a reality. We come from diverse backgrounds, united by a shared commitment to learning, collaboration, and steady progress. Get to know the people driving our missions. And then here we see, I guess, the founder team with these very nice animations. It goes from grayscale to color scale. But you can also see there are people that don't have a quantum background. So we have here, let's see. Oh, sorry, maybe I was off. So we have people with various different backgrounds. So engineering, we see, I think there's also some software development, I don't know if the backgrounds are different, but the tasks are very different. And we see a great team of people here. There's also some note here on the different investors. We see, of course, that Singapore is investing in there, but you also see Seeds Capital, for example, or State Farm Ventures, SG Innovate, I guess that's also Singapore. That one here, need to zoom in, Limtech Lee, PTE Limited. I haven't heard about that one yet, but yeah, you can see there are a couple of various different investors here. It says backed by top tier global VCs, half PhDs, half makers, blending theory and practice. I don't know why this is such an obsession, but the companies always like to talk about how many PhDs are working there. Also here it seems like there are a lot of PhDs, 18 scientists, engineers, and quantum theorists across 10 nationalities, so very diverse also in terms of nationality. And then experts in quantum error correction, FT compilation, I guess that's fault tolerance, and quantum circuits design. And then again, the call to action here to join the team and become part of the journey. With that, I think we are ending already today's journey. I hope you liked it. If so, please make sure to subscribe to this channel. And if you don't want to miss out, if you haven't had enough yet, of these companies, then make sure to check out our Hidden Quantum Champions playlist on the YouTube channel, where you can find many, many more of these company reviews. As always, make sure to stay hydrated and see you in the next one. Bye-bye.